IEEE is an international community of innovative members and volunteers, and it has four affinity groups: young professionals, women in engineering, life members, and consultant network through IEEE USA. So the members of these communities are typically interested in elevating their professional image, expanding their global network, connecting with peers locally, and giving back to the community. For the IEEE Young Professional Affinity Group is an international community of innovative members and volunteers that aims to inspire, energize, empower, and engage young professionals to envision and realize their dreams. Also, the Women in Engineering is a global network of volunteers dedicated to promote women engineers and scientists and inspire girls around the world to follow their academic interests in a career in engineering and science. So let's just get to know our young professional officers. Nazanin serves as the chair. Hassanta is the vice chair. Nitizam is the secretary. Nimasha is the treasurer. Dipanshu, Suprabha, Pranav, and Namrata serve as event coordinators for the Young Professional Affinity Group. Also for the Women in Engineering, Nazanin serves as the chair. Hassanta is the vice chair. Me, the secretary. Nimansha is the treasurer. Dipanshu and Namrata are the event coordinators. So if you are interested in volunteering with IEEE Women in Engineering and IEEE Young Professional, the best place to get started is with our Miami section affinity group. So the volunteering opportunities include coordinating events, mentoring, and or serving as an officer. So if you are interested in joining, please contact me through my email or my WhatsApp number. So finally, if you want to get updates on our events and activities, please try to follow us on our social media. We have different platforms for young professionals as well as for women in engineering. We have platforms in LinkedIn, Instagram, and Facebook. So let me introduce our today's speaker. Dr. Daniela Radu is an associate professor in the Department of Mechanical and Materials Engineering and NASA CREDO and NSF Prem Center Director. Dr. Radu, background covers a broad range of disciplines, and she's combining material science with chemistry and nanotechnology to synthesize novel materials with properties that enable their application of renewable energy. Dr. Radu holds a PhD in chemistry from Iowa State University and has further completed a 2-year postdoctoral fellowship at Scripps, California. Prior to her academic appointment, she has been a senior scientist at DuPont, where she developed a novel technology for thin film PV using earth abundant materials. Dr. Radu authored over 30 journals articles and more than 30 conference presentations and has 5 granted patents. Her research is funded by NASA, Department of Defense, NSF, and USDA. So before giving the speech to our speaker, Dr. Radu, please make sure to write down in the chat box your questions. And so today, not holding you any longer, thank you very much for being with us, Dr. Radu, and the speech is yours. Thank you.
Thank you so much, Ibtisam. It's very nice to meet you all. And I think this is my second participation with IEEE, and also this is a joint event with the Women in Engineering. And I'm really, really happy to see that you guys are extremely active in organizing events. I just only wish that next time we meet in person. So right now that we can. So I am going to share my screen. Just give me one little second. make sure I put my slides at the very beginning of the presentation. Okay, there we go. Okay. Can you see right now the full screen?
Yes.
You'll probably have to minimize the, I noticed the screens, the slides are a little bit bigger so that you have your participants screen open and probably will cut through that. So I'm going to minimize the mine so I can see the slides and you're gonna see the slides. So once again, thank you very much. I am, as Idrissa mentioned, the director of the Center of Research and Education in 2D Optoelectronics, and we also recently received funds from National Science Foundation to launch another center that is focused actually in quantum materials. And I'm not going to speak about that today, probably at another time, because this is also a quite cutting edge topic these days. I selected a title which is quite general, but it's sort of allude to the fact that we are living nowadays in the nanotechnology era. And I will speak how this pans into my particular research projects, but also what we do at Credo with nanotechnology. Oops. Okay, so when working in space, and especially when you want to create a spacecraft that survives deep space, you ask yourself a question about what are the technologies that you're going to utilize for that matter. And here there is a short bullet point list. First of all, you will need systems to live and breathe. You need proper propulsion. You need the ability to hold off the heat, right? You need protection from radiation in space, which is quite significant. I'm sorry. We're back there. And you need constant communication and navigation. If you think about all this, right, everything needs energy to sustain all these systems, right? So first and foremost, I should say the point of what is the point of going to the moon? Well, this is on the bottom of the slides. We have the Artemis logo. Artemis is a NASA mission that focused to bring the first woman and the first person of color to the moon. In the way, for NASA per se, in the way, preparation for going to Mars. So all these things that we are developing, we have to put a lens of survivability in space, okay? So if I have a cell phone right now, these cell phones will have to withstand radiation, heat, very, very cold temperatures, gravity, right? So that's going to fly in the space, right? So we have to have a way to hold it tight. So a lot of questions are around what we want to do with all the technologies that we have, that in such a way that they are still sustainable on the moon surface, and presumably learning all these lessons in order to move into the next leap into Mars. So again, going back to the sources of energy, obviously one of the most critical one that you could use in space, and the International Space Station survives in terms of energetics based on the sun, so the solar panels. So going from the moon, why the moon? Now we have to ask ourselves, why is the sun so critical? Well, the sun, first of all, is the highest, and this is a scaled map of energy resources. Within the sun's sphere, right here, we also have other options for renewable energies. And on the right-hand side, in the dark, if you want, we have the finite, except for the wind, of course, the finite resources, you know, the coal, the uranium, the petroleum, natural gas. So you can see that actually the sun is giving us per per year 23,000 terawatts, right? And we need for the war, that's an estimate on 2009, which obviously didn't go that much. Let's even if you double that, you still just need a mere 30 terawatts of energy for the world. And you do the math, right? And you see how much the sun is giving into in 1 year. You have more than enough just from the sun. So that's the motivation I personally felt very, very attracted in working on solar technologies. So in order to harvest the sun, and I'm speaking here, most of you being electrical engineers, you are quite, savvy in understanding the photovoltaic effect, so that you basically illuminate a material, and that material, so when a photon goes in, an electron comes out. So that's simple as that. However, how do you actually materialize that in a technology? So the first generation of photovoltaics, or PV, solar PV, so to speak, that have been discovered and explored were the single crystalline and the polycrystalline silicon. These are the solar cells that are the components to those solar panels that you see on our garage in the energy complex. And the multi-junction cells, which use a very sophisticated technology, very high efficiency solar cells, which are the ones that actually power, as I mentioned earlier, the International Space Station. Those are extremely expensive, not definitely affordable for the regular citizen, but extremely efficient and with very, very low potential for failure. Now, the single crystalline silicons, which if you want, they are the down-to-earth version, these guys are literally brittle. So if you ever hold a silicon wafer in your hand and have, you afford to crack that, you will know that it's just as simple to crack as a cracker, okay? So without having that fragility, automatically it's posing the question, can I do better in that realm? So the next generation that did exactly this, trying to solve that problem of brittleness, of lack of flexibility. So there are a couple of technologies that have been explored, and in fact, I should say they are still explored. The first one was trying to build on the crystalline silicon learnings and try to build thin film silicon. So these were just simply evaporating some silicon on flexible substrates. It didn't work out that well. There's lots of defects and everything. At the same time, what we call chalcogenides, which means there are materials that have the group 6 in the periodic table, sulfur, selenium, tellurium in compositions. This type of compounds are excellent solar absorbers. Okay, so I'll elaborate a little bit on that. Now, having said that, these are also bulk materials, so just like, is really chunk stuff, right? So that how people started to, how do you want to develop a technology from something that is just basically a big chunk of material? Well, nanotechnology came to the rescue, and about more than 1.5 decades ago, people started to elaborate these materials as a nanoscale. So we learned how to make nanoparticles from cadmium telluride, from copper indium gallium selenide, from the other chalcogenides listed here, copper zinc tin sulfide and copper tin sulfide, and even from amorphous silicon. So I want to just point out, and I will have most of my presentation about the nanoparticles and nanotechnology as applied for Gen 2. But I just want to point out real quick the fact that there are these emerging PV technologies. And more recently, one of the very, very significant one is the perovskite type of materials. And the perovskite type of material made a lot of noise, if you want, in the last couple of years, building from very small efficiencies, like 2 or 3%, and I'm talking about energy efficiency, power conversion efficiency, that is, to all the way to close to 20%. And when they are combined with the crystalline silicon technology, they can lead to 30%. The 30% is somewhere that would work in space. So that's why we are actually working right now to NASA to understand how to combine crystalline with either second generation, so a combo of these two, hybrid, what we call that, or a hybrid between silicon and the perovskite or dye-sensitized solar cells. So this is in the realm of multi-junctions, okay? But let me elaborate a little bit on the nanotechnology, because as I mentioned, this is what brings a lot of innovation. That nanotechnology enabled a lot of electronics and optoelectronics technology. So obviously, speaking to a group of electrical engineers, most of you, I'm not going to have to say too much about this, but bottom line is that we have a PN junction on these solar cells architectures that we're talking about, where the photon comes from the sun, it gets absorbed in the depletion hole, in the depletion region between the P and an N-type substrate, layer. And of course, after the photon is absorbed and I create an electron hole pair, those dissociate the electrons. The electron will just be collected at the top electrode and the hole at the bottom electrode. And basically you will have an electron flow. So you create electricity. That translates in a very simple architecture for this, for example, this chalcogenide copper indium gallium selenide, which it's nothing but a bottom conductor of molybdenum. Then the absorber layer, the CIGS, and fun fact is that, you know, if you Google that stuff, it's going to end up giving you some cigarettes information because it's shortcut is 6, unfortunately. Then we deposit a nano layer of 70 nanometers of cadmium sulfide, and this is the N-type layer here, which is a very thin because it has to be transparent. And then we have a transparent conductor at the top, which is typically your indium tin oxide or fluorine dope tin oxide, FTO, any type of TCO, transparent conductor oxide will work. And this particular cell is actually one of the previous records. Right now it's around 26%. But this is a Fraunhofer Institute in Germany, which is a 22.6% efficiency solar cell. And you see, it is quite simplistic if you think. So you have the molybdenum, which is done by sputtering, by the way, so that's a vacuum process. And then you have the CIGS, which is deposited originally by sputtering and subjected to an annealing process, which creates these large crystals. You need the large crystals for the continuum, for the electron flow. And then you have this cadmium sulfide layer and the transparent conductor. The problem is that those two materials, those two elements here, indium and gallium, are quite scarce in the solar crust, right? And so people try to see, okay, can I do something else? Well, before moving to what else we can do, I just want to show here where this CIGS stands. This is in green. Everything about thin film, the Gen 2 that I mentioned earlier, is in green. The emerging PV is in orange here. And you see the green are actually making up pretty high, 23%. In fact, the most recent record that I've heard of is about 26%. So this is not from this year, but every 2 years, the NREL puts up a map like this. NREL stands for National Renewable Energy Laboratory, which is located in Colorado. And they are putting this map, updated map every year together. The reason I mentioned that is because there are a lot of companies in green here that picked up on CIGS, and then one of the sudden we have this orange here, the perovskite that came in, and that was very little investment in continuing improvements on the CIGS. But the hope is not lost. And there is another reason why people were not that crazy about CIGS anymore, which is about the chemical elements abundance in Earth crust, as I mentioned earlier. So what other elements could be, if you think about And now I'm going to get into a little bit of chemistry. I know most of you are not crazy about that, but it's just quite simple, just looking at this periodic table, which is showing, in fact, the continental crust elemental abundances. Actually, we had to normalize to silicon because we have so much silicon. All the sand in the universe is silicon dioxide, right? So that, imagine how much silicon we have. So silicon obviously is basically reduced to this factor. So everything is compared with atoms per a million silicon atoms, okay? So take it with a grain of salt, grain of sand. Anyway, so I was talking about indium and gallium, right? And when I said we get a little bit of chemistry, these guys are in the same group, but we can combine elements on this axis or combine elements on this axis. Now, this cadmium is not that appealing, it's a toxic element. What if we get these gallium indiums replaced by zinc and tin? Okay, so they basically, the charge is going to be off. These are 3, 3, this is 2, 4, right? So let's see what happens. Well, when we do that, okay, so when we get indium and gallium replaced by zinc and tin, we observe from the crystalline perspective, crystallinity of the material, it's an isostructural, in other words, exact the same structure material. Wow, that's amazing. Well, honestly, it's like you look at your car. If you see another car, you would assume that it will work in the same way. And that was a big news, like having this isostructurality would imply automatically that things will go in the same direction, okay? So mentioning earlier the CIGS was produced through vacuum methods. They obtained a mere 9.15% for this copper zinc sulfide when they use vacuum material. Okay, so unfortunately, another problem was that this stack of elements had to be selenized in a gas. This is a little gas, hydrogen selenide, okay? So that there were many, many problems to making these materials, copper, zinc, tin sulfide, no matter how nice and isostructural and composed of very, very high abundance elements on Earth crust, it would not be a sustainable process. The material is great and sustainable and green, but the process is a disaster, okay? So what do we want to do with that? We had to find a solution. So what if we depart from these vacuum methods? What if instead of getting all these three metal stack elements, we actually create a nanoparticle that combines everything in this one nanoparticle, combines all the elements into this compound. And we were successful doing that, okay? So we were successful to synthesize nanoparticle with this composition. I always use this comparison with chocolate chips, you know, whatever you like, white chocolate, milk chocolate, chocolate chips, or even caramel chips. That is what the nanoparticles could be vision. If they are put on a layer, coated on a layer, and with any kind of deposition method, and this is a little bit technical, but on the other hand, you think about that, you can basically use any kind of method that gets a solution into a layer, right? So that most of you probably had some sort of clean room understanding or experience or training. So you basically do a coating with either spin coating, doctor blading, or even spray coating, like just the way we spray cars. And so you spray these nanoparticles that are dispersed in a solution, and you make a film. This is an atomic force microscope image before. I'm so sorry, I showed you after. So this is a before, so these are your chocolate chips. And because of nanotechnology enables the materials to behave in a completely different, it's just like, you know, the quantum realm, right? So everything is behaving differently at the nanoscales. The nanoparticles are extremely reactive. They are very small, and their surface area, the surface to volume area is very high. So therefore, they are very reactive. What that does is that when we want to melt these things, the melting point of a material, like for example, the CZTS material will have melt in bulk. So if I have a chunk, a big chunk of this crystal, and I want to melt it, it will take 1,000 degrees Celsius to melt. Well, guess what? When I operate at the nanoscale, these nanoparticles are going to melt at 350 to 400 degrees Celsius. Well, that's amazing that I can do that, you know, on a bench top. with some, environmental safety protection, whatever. But the bottom line is that I'm taking these materials, as I compared earlier with the chocolate chips, right? And I subject it to a 400, 500 degrees Celsius. This particular sample have been annealed at 500 degrees Celsius. And look what's happening. I'm jumping from about 20 nanometers diameter to about 1.5, 2 microns particles, large crystals, right? These are able to function in a cell, as I showed earlier, to conduct electricity. And there are some caveats in this film processing, because if I have a very good process, and this is where the frustration comes, especially in a graduate school, right? So that if you are working to get your solar cell done and you don't take care of your process, this is what happened. And I'm gonna again take advantage of the fact of this audience is quite savvy in electrical engineering. Now here you have a shunt right there, so that you're gonna have a short, I'm sorry, immediately, because you're gonna touch the top conductor with the bottom conductor if your layer is not nice and smooth and uniform, right? So this is a success story. This is not so much a success story, and these are actually two different companies. This is Solexant, which was reporting the process and patented, but they didn't get the solar cell efficiency, and the IBM, which had the world record of 12.6%. So this is a processing aspect of the solar cell fabrication. And no matter how great is your nanomaterial, no matter how great is your process, if you don't have a good understanding of the thermal phenomena, you can end up with a very problematic 0% efficiency cell. So this is something that what we learned from our first solar cells. I used to work for DuPont, and we created this very nice solar cell that had, in fact, an 8.5% efficiency, the one I'm showing here. But what we observe is that these nanoparticles are coming from the solution. They have some carbon on the surface, okay? So there is a lot of room for improvement when we work at the nanoscale, because in order to stop this thing to grow, you have to cap them. Once you cap them, you're gonna have that carbon layer, these little rays are gonna collect at the bottom here. And fortunately, they are conductive, so they are not gonna impair the actual functioning, but they are certainly not gonna give you a very good efficiency. And so we did Auger the profiling, and we see that this actually is carbon in here, And then so there is a lot of process to improve this, right? But as far as I am concerned, I started to get interested in improving the process by moving a little bit even more than a nano, in a nano to the nano realm, which is atomic thin layers of materials, right? And why is that? Well, a recent paper from Caltech indicated that if I go from bulk, okay, to one layer, I'm gonna increase at the same band gap, on the same exact band gap. If you look at these materials in this realm, CIGS and perovskites, if I go for one layer, I completely increase, almost like this logarithmic scale, I increase tremendously the absorption coefficient efficiency. So I absorb more light if this material is at a very atomic scale. Okay, so this is a very attractive way. So the question is, can I transform that CZTS in a nanosheet material? Okay. So first and foremost, remember we've talked about melting the materials, right? So in here, in this 2D materials, we are aiming to do that just from the very touch, from very contact of the sheet, of the nanosheets. So we don't want to anneal that anymore, right? So no more thermal treatment. And in fact, when people use quantum dots, instead of nanosheets with quantum dots, they already had a 10% efficiency. And this is developed by Ted Surgeon in Canada using colloidal quantum dots. And in a solar cell without thermal treatment. So that is somehow one of our goals right now. And this is one paper that we recently published, where we took basically taking to make this copper zinc tin sulfide. We started from something that we knew that is forming nanosheets not nanoparticles, which is thin selenide. And in solution, we added copper. We upgraded this, if you want, to the copper tin selenide, which is itself a solar material, but not as good as copper zinc tin sulfide selenide. And we added the zinc, and we obtained these nanosheets. And recently we published a paper where we got the solar cell where copper zinc tin sulfide is used, and in fact is used as a cathode in a dye-sensitized solar cell and performs better than platinum. So this is another, if you want, dimension of nanotechnology when we take things in just the 2D, okay? Going back to what my thoughts were about relative abundance, right? We are still trying to get the efficiency as high as possible, right? And we are still in the quest for materials that can deliver that. And in this quest, we found that there is a class of materials called solvenites, which are utilizing, in fact, copper, which is superabundant, sulfur as well, and one of the elements in group 5, whether vanadium, niobium, and tantalum. And you can see that vanadium is, to my surprise per se, when I first read about that, I was very surprised. Vanadium is actually one of the very abundant elements. So when we talk abundance, means obviously sustainability. So we can get, if we can get a product out of this material, we're going to have supply of starting materials for good, right? So it's quite abundant in the earth crust. So this class of materials that have copper, and as I mentioned, a group 5 metal and selenide, these things are actually having all of them, all these 9 materials, possible materials, have very nice band gaps, energy band gaps, which makes them suitable for optoelectronics, okay? So they are all in the sweet spot, either solar absorber or light emission or transparent conductors, okay? So we started with, again, trying to adapt what we learned about earlier about this copper zinc tin sulfide and create nanoparticles from solvenite copper vanadium sulfide, and we obtained, this is the structure of the material, and we obtained successfully nanocrystals, and we published this for printed thin film photovoltaics. But again, the fascination of working at the 2D, in the two-dimensional realm, right? It's great. So we are actually recently looking into how to create solar cells with copper vanadium selenide in 2D. And what is the most interesting about this material is that this should not form nanosheets. So again, it's a miracle at the nanoscale that this material can crystallize in quasi 2D morphology. So, and on the other hand, the immediate neighbor, the niobium compound, forms nanocubes, does not form these nanosheets. And this is really a puzzling question that we are looking at. So I'm just trying to explain to you, in principle, what is our research evolving in, that everything involving nanotechnology for this renewable energy and optoelectronics. With that, I want to shift the gear because I think I only have a little bit left I want to leave time for questions. And as I mentioned at the beginning and in the introduction, we are having this center at FIU, and we want to basically develop a center of excellence in research and education that is tied into the NASA mission, while employing and training students so that they are ready for employment with NASA. And we have various goals here. I'm not going to go on and read everything, but the most important, I think, that would be important for you as well is our focus on developing the STEM professionals in goal 4 and the research capacity of FIU so that you can conduct meaningful research. And so speaking of research, we have three research trusts. One is where I play a role is the chemical transformation in these 2D chalcogenide materials for a variety of applications, including photovoltaics, optoelectronics, and even superconductors. The second trust is looking into mechanical integrity of the materials in polymer composites, where we actually create composites with these 2D materials and try to understand their resilience. And more recently, we had some nice results about these materials are actually radiation shields in space. So that is really, really a nice outcome. And then this truss that you're probably more familiar is basically in the antenna where Dr. Bolakis is working with us on millimeter wave communications and CubeSats and wearable electronics. So it's a large variety of topics in this center. And if you have any interest, please talk to me and Edwimar anytime. So we also look into 2 more factors in terms of an education perspective is education core and a capacity building. And so in the education core, we have a lot of internships for undergraduate students. In the capacity building, Edwimar actually, she is the associate director for outreach, and she developed and implemented a lot of activities with the schools in Miami-Dade area. And so we are trying to make a ecosystem in South Florida where the students can come and learn about NASA and conduct internships and learn about opportunities for employment at NASA. So with that, basically, I want to point out that we have internships at NASA Center, so that especially that's are mostly for undergraduate students. And also we have internships at FIU NASA Credo, where the students spend a semester or 2 in the lab with the faculty mentor, part of our leadership team. And this is our most recent flyer that we had for NASA internships, where the students go 10 weeks and spend at the NASA Center. We have students that went to Langley, they went to JPL, are going to JPL, I'm sorry, this summer finally is in person, and NASA Glenn, and of course at Kennedy Space Center next door in Orlando, in Cape Canaveral. With the summer undergraduate research experience, we call it NASA SURE, summer undergraduate research experience, and we basically provide this experience for undergraduate students at FIU. We disseminate all these efforts in our website, which I invite you to consult, and we have, of course, a very, very strong presence in social media, which is maintained by Edwimar, and I would very much ask you to go and like our events and activities, and definitely this event is going to be highlighted on all the platforms that we have. And with that, I would like to thank you. Oops, I have my thank you slide. Yeah. I want to thank you, and I will take any questions that you might have.
Thank you very much, Dr. Radul, for the interesting information. Personally, I learned a lot. So we have one question in the chat. Says, could you please explain a bit about perovskite materials?
Sure. Now, when you ask me the question, are you asking about the performance of the solar device and the perovskite materials, or the materials in terms of their structure?
My question is mainly regarding the structure and what are perovskite materials and how they are used.
Right. So I guess that could be a complete full-blown presentation that we can already subscribe for next year. And hopefully we'll have some perovskite solar devices working. So the perovskite materials are nothing but another chemical compound, okay? And so I'll give you an example. A fully inorganic perovskite will be a cesium lead iodide or cesium lead bromide, and that goes in a ABX3 or ABH3 structure. So 1 cesium, 1 bromine, and 3 iodine or 3 bromine, so whatever the halogen is. And in principle, the perovskite material is an ABX3, but those that are used in photovoltaics generally are the halide perovskite, so that you always have a halogen involved, whether it's fluorine, chlorine, bromine, or iodine, or mixed halides. So there are perovskites that function in solar cells that are a combination of bromine and chlorine, okay? So the important thing about these materials that have exceptional solar absorption properties. And I can tell you that in the past 5 years, it was an exponential growth of publications because they went, as I mentioned, for low efficiency, very, very fast to the 20%. And now in tandem solar cells, they go all the way to 30%. The good news about the perovskite materials is they're also potentially processing solution, just like I mentioned earlier. So they are prone to flexible substrate as well. And so in principle, it's a completely different material in terms of how we process it. However, in the commonality of the two processes, that is, everything is done in solution. And when things are done in solution, I mean, obviously it's very, very cheap. A vacuum process requires all sorts of gases, evaporators, controlled atmospheres, very sophisticated pieces of equipment, where the solution process is just basically making almost like a coffee, right? So that is a solution that contains the perovskite, you coat it on a substrate, and you make a solar cell from that. And of course, it sounds so easy, but you know, at the end of the day, it's a layer by layer process, okay? So if you guys are familiar with OLEDs and probably, or LEDs, it's a very similar process, vice versa. So the perovskite learn a lot from the OLED. It's just the band alignment in the perovskite is exactly the opposite on the light emission in LEDs, okay? So that's where the attraction of this material is, that is, we can learn a lot from previous discoveries in electronic materials. And they have the whole transport, the cells, I mean, the perovskite solar cells will have an electrode, a top electrode, a bottom electrode, and in between they have a whole transport, electron transport, and in between is the absorber, the perovskite, okay? And so that's why I said we learn a lot from the OLEDs in this realm, if you're familiar with those structures, okay? And again, that is something that we are actually having another project funded by NASA just to look at the perovskite solar cells. And I'll be more than happy to talk next year at this event.
Yes, that would be great.
Or maybe in 6 months, I'm gonna push myself and my students and my group to get results faster. I have a presentation to make.
Yes, that would be great. Awesome. Thank you so much for wonderful information. We have more questions from the audience, I guess.
Yes. Yeah. So the question was, is the photonic band gap? Yes, that's what we're looking at, the optical band gap. That was one question. The other question is, there are tools. That's a good one. Tools that we can use for simulation. Well, it depends on what type of simulation. So that we can do numerical simulations like everything else that you do in electronics and materials. And we also do ab initio calculations, the DFT calculations for the solar materials to try to estimate things from the from band gap and electron transport, absorption coefficients. We can simulate these. And these are done in my group. We actually use DFT calculations. So this is ab initio computational material science or computational chemistry, if you want. My student is a physicist, so I should say computational physics, right? So, but definitely, I mean, when we talk about solid state materials, solid state physics, solid state chemistry, they pretty much mean the same thing. So we can simulate now, if you want. What one of the things that I would be interested personally would be the heat dissipation. I would like to see if anyone can model the heat dissipation, because as you can imagine, just like your phone, you forget it on the dash of your car, and then it's just getting hot, and all of a sudden there are problems. The same thing with these materials, right? So you want to make sure that when the sun is absorbed into these layers, right, the local heating is dissipated fast. So you're not going to have, just like, you know, my Mac right now makes noise because the fan is on. The same problems that we have in any kind of electronics is the heat dissipation. So that would be a very interesting simulation to do. But I'm not sure about specific tools, because we do a lot of synthesis and we do a lot of processing, but I don't do a lot of simulation in my group, except, like I said, this ab initio material science computations. Okay,
we,
so
yeah.
right. So, if you can get, so that's a very interesting question, because what we've seen, especially with these 2D materials, right? When it's just like when we talk about carbon nanotube or graphene. So graphene probably is a great example here. When we start doping these things, right? We switch quickly from a metal to a semiconductor to an insulator, right? So that if we are able to manipulate the band gap, what other application you can have if you have a material that is doped, just like we do with the indium tin oxide, right? So you get a very nice, if you have a very thin layer, you can think about building transparent conductors, novel transparent conductors. I should mention that one of the problems of the transparent conductors is that we still did not learn how to do that in a layer by layer in a very efficient way. So the transparent conductor, if you have learned of FTO and ITO and all that, you still buy those coated by sputtering. So they are still coated in a vacuum process. So we don't know that much how to do it in solution. I mean, we know how to do it, but we're doing badly. So that's why we still rely very much on a vacuum processing. So that if we are able to manipulate the band gap to get into a metallic, some of these 2D materials, to get them to conduct well, we can think about depositing this. Instead of getting a semiconductor, you have a transparent conductor. Another application is that you can use, if you manipulate the band gap in a proper way, you can capture, of course, in principle, you want to capture visible light. But if you think about mornings, UV light is powerful. In the afternoon, late afternoon, you have IR that is powerful in the solar spectrum. If you manipulate the band gap to capture in all this, in the entire spectrum, right, and build a tandem or even a triple junction, then you can basically capture more photons if you want, okay? So the whole point is that how can I get more photons into my material? Does it answer your question, Dipanshu?
Yes, Professor. Thank you. There's one more, I'm posting it.
I'm sorry?
You can unmute yourself and ask the questions.
Okay,
Yeah.
I think so. Yeah, thanks. Also, Professor, like you told about that crystalline solar cell.
Mm-hmm.
So I think still we are commercially using those crystalline solar cell. So what do you think is the future of a solar cell means? Will be able to completely replace these things with some better alternative?
So I can tell you one thing which I learned, unfortunately, the hard way, which I was working in industry and we started to work on this second generation of flexible solar cells. The problem is almost like, who was the first to step foot on in the industry, right? They had all the power and they unfortunately standardized the solar cells, the solar panel, if you want, in such way that the warranty has to be for 25 years. So that's what we all suffer, because the silicon solar cell can make it for 25 years. Even if I have the most outstanding thin film panel, it's going to be difficult. The cadmium telluride have been extremely successful and they are commercial, but not that much. First of all, of course, because of the cadmium issues that people are concerned, but also because of this kind of warranty, right? So that organic solar cells suffer tremendously. They're beautiful, colorful, they can be used in many applications, especially, the household application. But, you cannot put a warranty there more than 2 years, for example, because they degrade. So the materials that are in the composition of the solar cells matter. And of course, so far silicon does the best. But I do believe for the future, especially with this perovskite and chalcogenide tandem. So in fact, what that means is that you apply a thin layer of this perovskite or a thin layer of the chalcogenides on top of the silicon and develop some good encapsulation methods that you don't get moisture and you don't get oxygen to interact with the material, which are the enemies, if you want. then definitely we'll move into the direction to adopt this technology in the next decade. The problem with the silicon is that it's very heavy. I can tell you for sure that the cost of the silicon solar cells right now is mostly residing in the installation, right? So that we learn how to make these things very cheap, but the installation, the labor, you know, they have the people come on, put on your roof, clean them. The cleaning is a problem, especially where, you know, up north when we have snow and everything. I mean, we have the natural cleaning. You know, the problem with our hurricanes is that they can take the solar cell altogether, right? So have other type of problem, not the cleaning. But that's I think the if you want the long answer to your question is that the industry standards are currently the problem.
Okay.
Overall.
Okay, thank you, Professor.
You're welcome.
I have one follow-up question. You mentioned about organic solar cells. So I'm curious about how do researchers map photosynthesis with generating solar energy? Like, are there any research going on, like mimicking photosynthesis or using widely abundant material? Is there any work going on that?
That's a great question, and in fact, it's a complete. It's somewhat overlapping, but in the same time, different area of research. So that, you know, in the photosynthesis, you know, we basically get to absorb carbon dioxide and convert into oxygen, right? So it's a chemical process involved, and we learn a lot from this. So some of these perovskite materials, some of these chalcogenide materials, they also have photocatalytic effects. So not in the context of the solar cell, but in the context of the photocatalyst. So the same thing when you are able to split some of these. One of the applications is water splittings, right? So they take water and they convert in hydrogen and oxygen. So it's a huge area of research right now. It's a little bit of overlap, but not necessarily into the way we build currently our PN junction solar cells, you know. But it's a great area of research as well. And indeed, it's a lot of learning there that we can learn from nature.
Thank you so much.
Thank you so much.
Audience, yeah, I guess if you have more questions, you can unmute yourself and ask.
I have one question about the eligibility of international students for the internship you mentioned.
Right. So unfortunately, NASA has very strict rules about, unfortunately, even permanent residents are not eligible to participate at NASA centers. That is a citizenship requirement. However, we have, for example, if you do a research at FIU with a faculty member that is connected to our center, that is an opportunity for, you know, a summer or year-long internship, 1 semester or 2 semester internship with us. And Edwimar can give you more information about, presumably if you want to do that, then your mentor will have to get in touch with us, and then we can discuss with them a possibility for a project.
Okay, thank you.
You're very welcome.
Do we have more questions?
I think we don't have more questions.
Yeah, we don't have much time as well.
No problem. I won't go anywhere, and you can always come over, visit us, and we'll be very happy to entertain more questions. And we are very, very happy to come and talk to you guys.
Thank you so much. Thank you so much for accepting our invitation and for the wonderful presentation. And we had a great time with you. Thank you so much for making this time. And I have a request for all the attendees. If you can, please turn on the camera so we can have a group picture.
Just one moment. Edwimar want to say something?
Yeah, it was exactly like that. If they can put their camera on to take a picture.
Thank you so much. Appreciate. We'll definitely post this on our website as well. And very nice to meet you in person. I mean, virtually, and I would love to meet you in person as well.
We are looking forward for your in-person event. Thank you so much.
So 1, 2, 3, and I'll take a picture, okay? 1, 2, 3. We're good.
Thank you.
Thank you so
everyone.
much.
Thank
you
you.
so much. Thank you so much, Dr.
Bye-bye.
and Edmu.
Have a great
Bye-bye.
summer. Very productive summer to all of you. Bye-bye.
You too.
Bye. You too. Thank you so much.
Thank you,
Bye-bye.
Professor.
Bye. Thank you.
Happy summer.
Guys.
Bye.
Yeah.